So, in the last lecture we saw p-adic completion of Q that gives us the field QP, and we saw the ring of integers in that, it is called ZP, p-adic integers. We saw two descriptions of it, one using the notion of Cauchy sequences of rational numbers in the p-adic metric, and another using a very explicit description in terms of something like a power series ring. It is not exactly a power series ring, but it sort of has a feel like a power series ring. Today we are going to see p-adic completions of number fields. Okay, so let K be a number field and P be a non-zero prime ideal in OK. Recall that we have the notion of p-adic valuation, and what does it do? Well, it takes valuation of alpha, alpha is not 0, let us say valuation of 0 is of course 0. This is equal to, let us say, norm of p to the minus m if p to the m is the largest power of p dividing the ideal alpha. Okay. So, m could be negative as well. It just means that when you write the fractional ideal alpha as ratio of two integral ideals, p to the m, p to the minus m is the largest power appearing in the denominator of so p to the m is the p to the, if m is negative, then it means that it appears in the denominator when you write alpha as a ratio of two integral ideals. Okay. So, Kp denotes completion of K with respect to this metric dP, which is given by valuation of x minus y with respect to P. Okay. So, explicitly Kp is equivalence classes of sequences. So, An is a Cauchy sequence in K, right. What does a Cauchy sequence mean? This means that, let me recall what a Cauchy sequence is. For any epsilon greater than 0, there exists n such that valuation of An minus Am is less than epsilon for n m bigger than n. Okay, so that is what a Cauchy sequence means in this case. Now, so as I said last time, for QP it is a fact. So, here is an exercise. This exercise is very similar to what you learn for construction of real numbers. Kp is a field. All right. Oh, sorry, I forgot to say that this is up to equivalence relation. Okay, this is up to equivalence relation, and two Cauchy sequences are equivalent if their difference converges to 0. Okay, so you have to show that Kp is a field in this exercise. Now, there is a natural injective map from K to Kp. And what is this map? If I start with any element alpha in here, I want to produce a Cauchy sequence, right? And the Cauchy sequence is that it's just constant sequence, right? So, constant sequence. So, that is what that is a so you know, technically speaking, you do not take a Cauchy sequence, but you take equivalence class of this, right. So, equivalence class, all right. And so, you can show that this map is an injective homomorphism, a field homomorphism from K to Kp. Okay, so, that is how K is a subfield of Kp. Okay. And then we define O sub p to be set of all maybe before that I said all these things for Qp, but let me do it more generally for Kp. So, let An be a Cauchy sequence in K. So, I will call this A. So, I can define, right, I can define the valuation on A to be supremum over n valuation of An. Okay. And here is an exercise. This thing is a valuation, a multiplicative valuation on Kp. So, there are two components to this exercise. First of all, I defined this valuation in terms of Cauchy sequences. So, you have to show that if I take another Cauchy sequence which is equivalent to the one that you have taken, then the valuation is independent of which the supremum of these two Cauchy sequences is the same. Otherwise, we do not get a function from Kp, we just get a function from the set of Cauchy sequences. Kp is not the set of Cauchy sequences, it is the equivalence class of Cauchy sequences, right. It is the set of equivalence classes of Cauchy sequences. So, that is the first thing. Then the second thing is to actually show that it is a valuation. Well, there is a third point, whether the supremum exists or not, and you should be able to prove this using the fact that you have Cauchy sequences. So, I am giving all these as exercises because you see similar statements for real numbers in the construction of real numbers, and you just have to repeat those proofs. You do not need any new idea to prove these to solve these exercises. Okay. Now, so we have a valuation on Kp, right, and I can define OP in it to be all A in Kp such that valuation of A is less than or equal to 1. Okay. Now, this does not have a, well, I mean, you can take a subset of real numbers satisfying this, but that is just the closed interval from -1 to 1. Okay. It does not have any algebraic structure as such, but in this particular case of p-adic valuation, here is a proposition. The reason I did not prove all these things for Qp because we are doing it here in general. So, OP is a subring of Kp and OK is contained in OP. Okay, so here is a proof. What does it mean to say that OP is a subring? So, if alpha and beta are in OP, then we must show that alpha plus minus beta and alpha beta are in OP, okay, and we need to show that 0 and 1 belong to OP. So, 0 and 1 is fine, because what is the valuation of 0? This is 0, and valuation of 1 is equal to 1. So, this is fine. 0 and 1 are in OP. Now, if alpha beta are in OP, then I consider valuation of alpha times beta. This is valuation of alpha times valuation of beta, which is less than or equal to 1 times 1, which is 1. So, hence alpha beta is in OP. Okay. Now, what next? If alpha and beta are in OP, then valuation of alpha, let me write it together, plus minus beta. Now, this up to this point everything works for any valuation. Now, this is a main point for which you need that it is a non-Archimedean valuation. So, this is less than or equal to max valuation of alpha, valuation of plus minus beta, but valuation of minus beta is same as valuation of beta. So, this is less than or equal to max of 1 comma 1, which is equal to 1. Okay. Hence, alpha plus minus beta is in OP. Therefore, OP is a subring of KP. And when we proved that any non-Archimedean valuation has a prime associated to it, we proved earlier that if alpha belongs to OK, then valuation of alpha is less than or equal to 1, right. Hence, OK is contained in OP, right. We take this natural map from K to Kp, which sends any element of K to the equivalence class of constant sequence as an inclusion. We identify K with its image, and that is why I am writing the inclusion sign here. Okay. So, these are technical things that by the time you take an advanced course such as algebraic number theory, you should be well aware of, because these are the things that one learns in the first analysis course. Okay. Now, here is an exercise. So, that proves the proposition, but here is an exercise. So, find what Z sub P intersected with Q is. Okay. We know that Z is contained in ZP intersected Q, okay. But Z is strictly bigger, Z is strictly smaller than ZP intersected with Q. So, you want to find what exactly are the rational numbers with valuation less than or equal to 1. Okay. So, this exercise will really help you understand valuations and p-adic valuations and what it means to say that something has valuation less than or equal to 1. Okay. Now, what I have is this contained in Kp, and then this contains K, this contains O, K, and then here I have P. So, what goes here, right? So, here is a P sub P, this is set of all alpha in OP such that valuation of alpha is strictly less than 1. Okay, so, this is definition or notation, and here is another proposition. P sub P is a prime ideal in O sub P. Okay. And again we kind of just follow the proof. So, if alpha and beta is in P sub P, then valuation of alpha plus beta or plus minus beta if you like is less than or equal to max valuation of alpha, valuation of beta, but they are both less than 1. So, this is 1, hence alpha plus minus beta are in P sub P. Next, if A is in OP and alpha is in P sub P, then valuation of A times alpha is equal to valuation of A times valuation of alpha, which is less than 1 times 1, right. So, it is less than or equal to for A and it is less than for alpha. So, you get less than 1 times 1 and hence A times alpha is in P sub P. Therefore, P sub P is an ideal in O sub P, but why is it a prime ideal? If alpha times beta belong to P sub P for alpha and beta in O sub P, then valuation of alpha beta is less than 1, but on the other hand this is valuation of alpha, valuation of beta. Therefore, either valuation of alpha is less than 1 or valuation of beta is less than 1, right. Hence, hence alpha belongs to P sub P or beta belongs to P sub P, and therefore, P sub P is a prime ideal. Okay. So, now we can complete this picture we had. So, you have Kp that contains OP. So, Kp comes from K, OP contains OK, and here we have P and here we have P sub P, right. It is clear that P is contained in P sub P, that is how we constructed our prime ideal P starting with a non-Archimedean valuation. Okay, fine. So, here is a lemma. It's kind of somewhat tricky if you have not seen these things before. If I intersect P sub P with OK, right, what do I get? And the answer unsurprisingly is P. A word of warning, P sub P intersected with K is not P. So, if I take intersection with K, then it is strictly bigger than p, it is not equal to p. This is related to this exercise of what is ZP intersected with Q. Okay. Now, how do I prove this lemma? So, it is clear P is contained in P sub P intersected with OK, because P is contained in both P sub P and OK. Now, let alpha belong to P sub P intersected with OK, right. Then valuation of alpha is less than 1 because it is in P sub P, right. And remember, P was constructed, I mean, okay, remember, maybe I'll say it this way. P is equal to all x in OK such that valuation of x is less than 1. Okay. Again, a word of warning, P is not equal to all x in K such that valuation of x is less than 1. Okay. That is a strictly bigger set than this. So, here let me write this as a warning. P is not equal to x in K such that valuation of x is less than 1. Okay. Hence, alpha belongs to P, right. So, that proves the lemma. Okay. So, now we can consider the following function. So, OK is contained in OP and there is a projection from this to OP mod P sub P. Okay. So, I get a map from OK into OP mod P sub P, right. What is the kernel of this map? The kernel of this map is P sub P intersected with OK, which we proved is just P. Hence, we have an injective map, injective ring homomorphism OK mod P to OP mod P sub P, and my claim is that this map pi is also surjective. So, OK mod P is isomorphic to OP mod P sub P. Okay. So, how do I prove that this map is surjective? I start with any element of OP and I want to show that I can change it by some element in P sub P to actually give me an element in OK, right. So, once I do that, I'll get that this map is surjective. Okay. So, what do I do? So, let AN belong to OP, right. Okay. So, therefore, AN is a Cauchy sequence of elements in OK, right. And furthermore, right. So, this means that valuation of a n minus 1, for example, goes to 0 as n goes to infinity. So, in particular, this means there exists n such that valuation of a n minus 1 is less than 1 for n bigger than or equal to capital N, right. And so, what I can do is so what I can do is I can change my so if I have a1 and so on up to an plus 1 etc., you can subtract something like 0 and 0, this is n terms, and then after that you can take what do I want to do? an plus 1 minus an plus 2 minus an, and so on. So, this is an element in P sub p, okay, and right. And once I subtract this, what I get is something like a1 and then an etc., and so I can right, then I can show that this is equivalent to an element to a1 up to an and then zeros after that. So, this is an element in OK plus an and so on, which is also an element in OK. Okay, so that is how you show surjectivity of this map. Okay. So, so what does that mean? So, we have, so this means that OP mod P OP is a finite field, right. So, OP is an uncountable ring, but when you take this modulo this P mod P sub P, you get a finite field. Okay. So, in particular P sub P is a maximal ideal in OP. Okay. And here is an exercise. This is perhaps a little bit more difficult than the other exercises I gave today. So, P sub P is the unique maximal ideal in O sub P. Okay. In fact, you can also show, so maybe first show this and then show that P sub P is the only non-zero prime ideal in O sub P. Okay. All right. And then the third exercise you can show is that P sub P is a principal ideal. So, it is generated by one element, and that gives a very nice structure to this ring O sub P. Okay. Alright. So, what we did today was we studied p-adic completion of a number field in general, and then we proved a bunch of facts about it that I only stated for QP, but we proved them in general. So, in particular it also applies to QP. In the next lecture, we will look at an alternate description of K sub P, which looks like this power series description, or to the base P description, and at least that is useful to think about it, perhaps, even if not so useful for proving results. So, it may not be so useful as a theoretical tool. Okay, thank you.